We're going to look at another example of the greedy method applied in order to solve what's called the fractional knapsack problem. Now remember, the greedy method is a fundamental design technique usually applied to optimization problems in which we repeatedly make a locally optimal choice called the greedy choice in hopes that it will lead to a globally optimal choice. It doesn't always work in all situations, but it is guaranteed to produce a global optimal solution if our problem has a greedy choice property. So we're going to look at the knapsack problem. And the idea with the knapsack problem is that we have a set of n items. Each item has a positive benefit associated with it. This is a value, how much money it's worth. And each item has a positive weight associated with it. This is how much it costs to carry it. So this could be measured in pounds, or maybe this is even volume, milliliters or something. But I'm just going to call this weight. And let's say, imagine a scenario where a thief breaks into a store. Inside the store there are these n items, each one having a benefit and a weight. And the thief carries a knapsack which can hold weight at most capital W. And the goal is to leave the items so that the total benefit inside the backpack is maximized. There's a lot of applications of this, especially with resource allocation problems or with portfolio investment. For example, there's many options to invest in, but you have a limited budget. You want to find a way to maximize your expected return. This can also be used to figure out how to cut raw materials. You have to cut raw materials from a sheet of metal in such a way that wastes the least amount of sheet metal. And there's two variations of this knapsack problem. One is actually called the 0-1 knapsack problem. And in this instance, you can either take an item or leave it. You don't have the option of taking a portion of an item. And we're not going to look at this one today, although we're going to see it in a later video. And the other one, what we are going to focus on today, is the fractional knapsack problem, which is of all of these n items that we have the option of, if we want to, we can break some item up into smaller sized pieces. So we don't have to take, maybe this item weighs 5 pounds. Rather than taking all 5 pounds, we have the option of taking only 3 pounds, for example. You could think of this as maybe being the difference between if we had like gold dust, where we could just scoop out as much of that as we want, versus if we had a gold bar and then we would have to either take that bar or leave it. We couldn't melt it down or anything. So this is having to take an item or leave it is the 0-1 knapsack problem. If we can take a portion of that item, this is the fractional knapsack problem. And we'll see that we can solve this fractional knapsack problem using a greedy method, but we can't do that for the 0-1 knapsack problem. Okay, so with the fractional knapsack problem, since we can take only a portion of an item, so we could take none of it or we could take half of it or something, we're going to use another parameter xi to represent how much of some item that we take. So this is some value which is between 0 and however much weight wi that this item of this item that we have. So our goal is to maximize, this is the objective function we want to maximize. This is the total worth of, for each item that we have in our set S, we want to maximize the total worth of items. So this is how much each item is worth individually times the fraction of how much that item we take. But we're constrained by the fact that our backpack, the knapsack, can only carry at most capital W pounds. Okay, so let's see an example of this before we get into exactly algorithmically how we would solve this. So let's say we had these 5 items. Each one has a weight associated with it. Here we're just showing that in terms of milliliters, and a benefit. So note that this benefit is for all of this item. So for example, all 4 milliliters of item 1 are worth $12. All 2 milliliters of item 3 are worth $40. And we only have exactly 4 milliliters of item 1 to work with. We don't have infinitely many of item 1 that we could take. We only have 4 milliliters. And our goal is, we have this is our knapsack, some jar here, which can hold 10 milliliters. And we want to maximize however much of these items we can take, so that the goal is to maximize the total worth of items that we end up putting in this jar. And we can't exceed 10 milliliters. So how we should approach this? Well, because we're given the weight and the benefit, it wouldn't be appropriate yet to compare items based on their benefit alone, because, for example, it looks like this item 2 is worth more than item 4, for example, because item 2 is worth $32, item 4 is worth $30, which is less. But if we evaluate this per milliliter and kind of normalize it so that we see how much each item is worth per milliliter, we see that item 4 is actually worth more because it's $5 per milliliter. Item 2 is only $4 per milliliter. So our first step here is to calculate these values. So this is just a normalized benefit, essentially. So how much money per whatever unit of weight or volume that we're working with, how much benefit to weight, what the benefit to weight ratio is. So we have, given the weight and benefit, we've calculated this value here. So now we can figure out which one is worth the most and the least in terms of 1 milliliter. And this is how we're going to end up solving this. So we've got the item worth the most is item 1. And since this is worth $50 total, we're going to take as much of this item 1 as we can, which we can only take 1 milliliter of it. And now that we have the remaining 4 items to choose from, we're going to take the next most expensive per milliliter item, which is item 3, which is worth $20. And we've got 2 milliliters of that we can take. So each of those 2 milliliters is worth $20 per milliliter. So we take as much of that as we can. So now we've got 2 milliliters of that, and we filled up, let's say here's 1, 2, 3 milliliters, and we've still got 7 milliliters remaining. So the next most expensive item of all those which remain is item 4, which is worth $5 per milliliter. So we're going to take as much of that as we can. We've got 7 milliliters to fill up, and so that means we can take all of the 6 milliliters. And without drawing all of that here, let's say now our knapsack is filled to this point. We've taken 9 milliliters so far. That means we've got 1 milliliter left that we can fill it up with, since it can carry 10 milliliters. So of the remaining items we haven't taken, we're going to pick item 2 because that's worth more money, more value per milliliter. And we're going to take as much of it as we can. But in this case, we have 8 milliliters we could take, but we're constrained by the fact that we can only fit 1 additional milliliter in our backpack, in our knapsack. So we're not going to take as much of this item 2 as there is. We're just going to take as much as we can fit into our knapsack. So we're only going to take 1 out of the 8 milliliters that there are to take of item 2. So this is one way that we can solve this, and as it turns out, this is an optimal solution as well. So let's see kind of more formally, algorithmically, how did we solve this fractional knapsack problem. So our greedy choice is to keep taking the item that has the highest benefit to weight ratio, that was the highest value. So how this worked was we were given some sequence S. We have a knapsack which has capital W, this is the weight, the capacity of our knapsack. And our goal is to fill up our knapsack with as much stuff as we can take so that we maximize the total worth of the items that we took. Alright, so how we had solved this in the previous slide was we went through each item and then we calculated what this value was. So remember, value for an item was its benefit to weight ratio. So this is just a normalized benefit per item, how much dollar amount per weight. And we're going to keep track of also how much of an item we take. This is that xi. So initially we're just going to set this to be 0 for each item to indicate we haven't taken any item, we haven't put any item in our knapsack yet. And then we're going to increase this as we go along and we figure out which items we should take. So we go through each item and calculate its value. And then we also initially, just as a pre-processing step, say that, okay, we haven't taken any items yet. Now we're going to keep track of how much we've put in our knapsack so far. So initially, so this is our little w, what we currently have in our knapsack. We are constrained by capital W, which is the capacity of our knapsack. So initially we have nothing in our knapsack. Then, while we still have room left where we could put an item in our knapsack, we're going to take whichever item has the largest value and then put as much of this item with the largest value as we can fit in our knapsack. So how much we should take? We could take however much of that item there is, but we also have to be careful that we don't exceed the capacity of our knapsack. So how much room we have left in our knapsack is capital W minus little w. How much we have, the capacity of our knapsack minus how much we're currently carrying in our knapsack. And we're going to take whichever one of these is smaller, because if we don't have enough room in our knapsack, then definitely we can't exceed however much the capacity of our knapsack. And then also, if we don't have a lot of some item I to take, we can't take more than what that item has to offer. So xi is exactly how much of that item I that we're going to take, and we're going to update the current weight of our backpack with the new item that we're taking now. So this is just however much we were carrying in our backpack before, plus now we're taking item I as well. So what is the runtime of this? Let's look to see how many iterations we're executing here of our for loop and our while loop. So we've got in our for loop, we're going through each item in our set S. So we've got a linear number of iterations. This is because we have n items in our set S. And for each item, we do a constant time operation. We just set xi to 0, and we evaluate this expression and store the value in vi. So the total runtime of just this for loop is big O of n, is linear. Our next operation here is constant time. And then let's figure out what's the cost of the next portion here. Well, let's see first how many iterations we perform of this. So our while loop, we're going to continue through this while loop as long as we can fit items in our knapsack. And we increment little w differently depending on the weight of some item, whichever item we're taking next. But in the worst case, because remember, we're always going to evaluate something in the worst case, how many times would we go through this while loop? We can't possibly take more items than what we have to work with. So maybe we only end up taking a few of them and they fill up our backpack already, but in the worst case, we're going to go through each of the n items that we have. So in that case, we have big O of n iterations. Now the question is, how much does it cost for each of these lines? Well, we've got, this is a constant time operation, this is a constant time operation, but how much would it cost for this removing an item with the highest value? Well, it kind of depends. So there are some things hidden here just in this line for our pseudocode of how we're actually accomplishing this. Because if we were to just scan through our sequence each time, scan through our set each time, and figure out who has the highest value, then this would be just one call to this line would be a linear time operation, which would make our total running time quadratic. And that's not very efficient, and we can do better than that. So there's a couple ways that we could accomplish this. Prior to going through each item, we could, let's say, one option is we could sort everything in S by their values, VI. And once we have S completely sorted, then removing that item that has the highest value, this will just be, if we have items in ascending order, then the last item will have the highest value. So then removing an item, figuring out which item has the highest value, this would be a constant time operation, which means our while loop would be big O of n. However, sorting items, we know that if we're not making any other assumptions about the type of input that we have, which we don't know anything about the type of input, about the maximum value in particular of what integer value we could have. So that means that if we sort items, just that the cost to sort items is n log n. So our running time would be n log n. Or instead of sorting items, we could create a heap, a min heap, or max heap, create a max heap of all of the items that we have in S, using their values as keys. And we know if we use bottom-up heap construction, we can create a maximum heap in linear time. So just this one step before, we wouldn't repeatedly do these operations, we just do this once before our while loop. We could create a max heap in linear time, but then removing the item that has the highest value, this would then be a log n logarithmic operation. So this would still make our total running time n log n. So no matter which way we end up implementing this, if we use one of these options, 1 or 2, then our running time is n log n. Okay, so easier to design this, we just have some form of iteration here, and then we define our greedy choice. Our greedy choice here is we always pick whichever item has the highest value. More difficult thing to show now is, why does this actually produce a correct result? Why would this always give us a knapsack where we've maximized the total worth of items in that knapsack? And how we can show that is by proving that there is an optimal solution where we take as much of this item that has the maximum value as possible. This is, we want to prove this claim, which is to say that our problem has the greedy choice property. Our greedy choice is taking as much as we can of the item with the maximum value, and we want to show that there is an optimal solution which includes that. So in order to prove that this is the case, we can use a proof by contradiction, which means we're going to start off by assuming that this is wrong, and then reach a logical contradiction, which means that we were incorrect to assume that this was wrong. So in a proof by contradiction here, we're going to, assuming that this statement is false, instead, let's say there's optimal solution S, we'll call it, which doesn't follow this, where there's some item I, which has a maximum value possible, that item S doesn't take as much of it as it possibly could. Instead, that solution S doesn't take as much of it as it possibly could. Instead, solution S takes this item J, which isn't worth as much as item I, and it doesn't take as much of item I as it could. So that means that the value of item I, since has the maximum value, this is more than whatever item J is worth, but we didn't take as much of item I in this supposed optimal solution S as what we possibly could have. Instead, we ended up taking item J. And if we do that, then we could just substitute however much there was of item J in S with item I, with however much we can replace of item I. So we have, here's this optimal solution. We start off by assuming this is an optimal solution S, and it doesn't take as much of item I as it could have. It takes this, here's all of item J that it ends up taking instead. And so we're going to swap out everything that we can of this item J, since it's not worth as much of item I. We're going to change this solution and replace as much as we can of item J with item I instead. So how much we could replace, it just depends on how much there is of item J. So we can't, if item I, for example, we've got a lot of item I and we've only taken a little bit of item J, we can't replace more of item J than what we have of it. But also, if we've already taken a lot of item I, we know that there's still some left to take, but if we've already taken a lot of it and we've only got this little bit more that we could take, then we can't substitute any more than this amount, from item J. So this is just however much left there is of item I that we could substitute. So note that this could be a fractional amount. Right? This is kind of key why this proof only works if we're using the fractional knapsack problem. But by making this substitution, since item I is worth more than item J, then we end up getting an even better solution than what S had to begin with. But this is where we get our contradiction, that we started off by assuming that S was an optimal solution. So it shouldn't be possible that we can get something which is even better, then that means what we started with wasn't an optimal solution. So this finishes our proof that this is the contradiction that we wanted to obtain, which means that we have correctly proved our claim that there is an optimal solution where we take as much of the item that has the largest value as possible. And this is what our greedy choice is. Okay, I mentioned earlier that we can't apply the same greedy method to the 0-1 knapsack problem, and I just want to give you a quick example of that, because we're going to come back to the 0-1 knapsack problem again. So we have seen the fractional knapsack problem, so I'm just call this KP. The 0-1 knapsack problem is defined where we have the same set of items which have a benefit and a weight, but we can either take an item or leave it. We can't take a portion of it. Now you saw in the proof that we had for the fractional knapsack problem that we used that property, that we were allowed to take only a little bit of an item if we wanted to. But we can't use the same approach for the 0-1 knapsack problem. So suppose we had, let's say here's item 1, 1, 2, and 3. And let's say item 1 was worth $60. Item 2 was worth $100. And item 3 total was worth $120. But individually they weighed, let's say item 1, this is how many pounds they weighed. Item 1 weighed 10 pounds, item 2 weighs 20 pounds, and item 3 weighs, let's say 30 pounds. This is their benefit and weight. We can calculate their value, kind of normalize this per pound to where, all right, item 1 per pound is worth $6 per pound. Item 2 is worth $5 per pound, and item 3 is worth $4 per pound. So let's say this is our input. We just proved that we can solve this optimally if we were solving the fractional knapsack problem. We would take first as much of item 1 as we can, then as much of item 2, then as much as item 3. But let's see why this wouldn't work if we were trying to solve the 0-1 knapsack problem, where we can't take a fraction of an item. So let's say we wanted to fill a backpack. Let's say this is our backpack, where we can hold, let's say 50 pounds. But we can either take an item or leave it. If we were to try and use the same greedy approach, we would end up taking as much of item 1 as we can, which means we take, let's write it this way, 10 pounds of item 1. Now we've got 40 pounds left to work with. So we take as much as we can of item 2. We've got 20 pounds of item 2. And then we have 20 pounds left over. But since item 3 is 30 pounds, and we're not allowed to take a portion of it solving the 0-1 knapsack problem, then we wouldn't be able to take anything more. We would essentially have just this empty space in our backpack. So using the greedy approach, we would end up getting a total of $160 worth of stuff. This is how much item 1 plus how much item 2 is worth. But we could do better than this if we ended up taking instead, let's say, item 3, which weighed 30 pounds. So we've got 50 pounds. Oops. Hang on a second. So we've got item 3 is worth, or weighs 30 pounds. We've got a 50-pound backpack that we can work with. If we took as much of item 3 as we could, we'd have 20 pounds left over. We can use that 20 pounds to take item 2, and then we walk away with $220. So this is an optimal solution. And this is what our greedy approach would have been if we tried to use it to solve the 0-1 knapsack problem. So we can't use the greedy approach to solve this. We need a different way that we can solve that problem. And you're going to see that in future lectures when we talk about dynamic programming. But we can use the greedy method to solve the fractional knapsack problem if we were allowed to take a portion of an item. Okay, if you have any questions, post on Piazza, reach out and let me know.